All right, next we're going to do 5.15. So argon gas flows steadily with a velocity of 50 meters per second into an adiabatic turbine at 1500 kilopascals and 450 degrees Celsius. The gas leaves the turbine at 140 kilopascals with a velocity of 140 meters per second. The inlet area of this turbine is 55 centimeters squared. The power output of the turbine is 180 kilowatts. Determine the exit temperature of the argon. So this is a little bit similar to the compressor question we did with a couple differences. This is not a compressor, this is a turbine, so we expect a positive work output, not a negative work input. Secondly, again, we're given some information about velocities, so we know we can't, in this case, neglect anything related to the kinetic energy. We will have to calculate that. So let's start looking at the mass flow rate, for example, of this. Let's see if we can determine the mass flow rate, because we know we're going to need that in the first law of thermodynamics. So let's go here, new sheet, and I'll just keep it open on my other computer there. So what do we know about the inlet? We know the pressure and we know the temperature. And if it's an ideal gas, immediately that means we know the density. We're also given the area and the velocity. So we actually have everything we need to find the mass flow rate. Now this is argon gas, so it has its own R, which is its gas constant. And if you go in the tables on the first page, you look in, I think it's the third column for R values, look for argon, and hopefully you should find that R equals 0.2081 kilojoules per kilogram Kelvin. Okay. Now, we want to find either the density or the specific volume. So again, ideal gas law, pressure equals density R temperature. That means that density equals pressure over R temperature. And in this case, we're told the pressure is 1500 kilopascals divided by R, 2081. Temperature, again, we have to convert it to Kelvin, right? So we go from 450, we go plus 273, and we get 723. And let's see what the density is. I am getting density of 9.97 kilograms per meter cubed. Yeah, that's it, 9.97 kilograms per meter cubed. So that's the density. We know the area, we know the velocity. So m dot really simply is just going to be 9.97 times the area, which is 55 centimeters squared. So to bring it into meters, we have to divide it by 100 squared, and we'll get 0.0055 meters squared. That's the area. Rho AV. So V, we're told, is 50 meters per second, and immediately, sorry, no, that's correct, 50 meters per second. And immediately we can find that the mass flow rate is 9.97 times 0.0055 times 50, which is 2.742 kilograms per second. So we have the mass flow rate, but again, we're still trying to find the exit temperature, but we know we're going to use the first law of thermodynamics. And that means we might need the mass flow rate, especially since they give us the work output as a power and not a kilojoules per kilogram. So let's start looking what the first law of thermodynamics is going to look like. Again, this is a turbine, so Q is 0. We just have negative W. We have m dot, which we found already, so that's good. Change in enthalpy plus change in kinetic energy. Now, only thing is, we don't have property tables for argon, so we don't really know H2 minus H1, but we know that in any case, we have the relation that H2 minus H1 equals CP T2 minus T1, right? This is just basically it comes from the definition of CP. So with this in mind, we can substitute this guy instead of this guy. And if we know T2 and T1, then we're good to go. So well, actually, we're trying to find T2, but we know T1, we know everything else. We're able to solve for T2, which is what we're looking for. So let's start subbing everything in. So what's the power output? It's 180. It's positive 180, but the equation always we start with negative W. So it's negative a positive. So it's negative 180 kilowatts equals M dot, which we just found was 2.742 times this CP, which we can get from the table. Sorry, from the property tables. Again, it should be in one of the first columns on that first page. And CP is 0.5203 kilojoules per kilogram Kelvin. Now, then we have T2 minus T1. T1, we're told, is 723 Kelvin. Well, we're told it's 450 Celsius, but we're smart, so we know to bring it into Kelvin. And then V2 squared minus V1 squared over 2000. So V2 is 140. V1 is 50. And 2000, like this. And now it's just a matter of solving for T2 algebraically. And if we do that, we will end up with T2 equals 580.4 Kelvin.